This folder contains a couple of files, and one is basically well, let's open it up. It's a PDF file, and it's an article on standardization of data. At your leisure, you can read this. I'm not going to, I'm not going to pull any questions on the quiz or homework from this article, but it'll give you a little bit of a background into the idea of what standardization is, the difference between the direct method and the indirect method. Most people use the direct method these days. But really, the basic stuff that I think would be valuable for you to learn is what the impact of standardization is and why you might want to use it. So we're going to do an example of this with some real data. And this data was actually collected. I'm going to open this up. It's an Excel file. You can open it up with me if you want. By the way, if we have any kind of technical glitch and we get cut off or something like that, try and log back on wait a few minutes, just give me time to recover, and try and log back on with the same link that I've given you. If that doesn't work, go to Blackboards and the announcement section of Blackboard, and I'll post some advice on how we can get back in touch. But hopefully we won't have an issue like that. Okay, so this data is based on actual numbers from the New York City Department of Health vital statistics. Vital statistics, vital means life, so there are statistics that involve life and death and so on and so forth. You can actually dig this up. Let me see if I can't find it quickly. New York City, just to make sure that you understand I didn't make all this junk up. Vital records, how about that? Okay, no, we don't want that. Vital statistics summary. If you go in here, you can find annual report. I think this is going to be it. Here we go. So in this document, this is a PDF file that's published every year by the New York City Department of Health. In this document, they list all the statistics, many statistics for life expectancy in New York City, current life expectancy, mortality from different groups, for infant mortality, for various kinds of other health-related statistics and life-related statistics. And you can actually go through here and take a look at a lot of this information. Geographically, for instance, age-adjusted death rate for different boroughs and sections of boroughs and so on. So, and we also, here's the leading causes of death, 10 leading causes of death per 100,000 population in New York City. Ranked number 1 was diseases of the heart and so on and so forth. No surprise there. Diabetes was number 3, cancers number 2, and so on. We're not really that surprised by that, right? So here's leading causes of death for all ages, and then by different age groups. Okay, so if we wanted to, we could go through here, and we could see that I'm thinking that if I move this over, I'm going to be able to see this. They have statistics for males and females for the number of deaths that occurred during this calendar year, 2015, for males versus females, and I'm going to find cardiovascular diseases and so on. So that's under 1 year old. I think I ignored that. But for cardiovascular diseases of the heart or cardiovascular diseases, they have the number of deaths for males and females and the percentage of those particular populations. Okay. Also in here, you have the total. In the previous page, summary, you'll have the total populations of those groups in New York City. Okay, so you could actually go through here for each of these age groups. You could record how many people died. Notice that greater than 85 years, the number 1 cause of death is diseases of the heart for both males and females, and so on and so forth. So we actually could cull this data, and that's what we did. Okay, and we summarized it in this table. So I ignored the younger groups, very low rates of cardiovascular disease in the younger groups. So I ignored them, and I just started with the 24 to 40-year-olds, to 44-year-olds, and I summarized that. I found the population for that group. I found the number of deaths from that group from the vital records for females, and I did the same thing for males. This I think I took an archived version of it. I think it was back in 2003 or something like that. So you'll notice New York City population is quite a bit smaller than it was uh, 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 than it would be today. Now again, since it's only 25 and up, it's still quite a bit smaller than the total population. It's about 5 or 6 million total when you combine males and females. But I'm sure the population nowadays is a bit greater. You weren't able to log on there? What's that? Oh, okay. I'm saying, if I realized that there were going to be this many of us, I would have put it on the board behind us. But I guess if you guys can share that, it'll work out okay. Okay. So at any rate, I'm going to take a look at these deaths and see. I'm going to calculate the crude mortality rate. Well, what do I mean by crude mortality rate? Well, I'm going to take a look at this. I'm going to say that the mortality rate for females is going to be equal to the total number of females that died divided by the total number of females that were alive at that time. So that the probability of dying if you're a female in this population during that year was about 0.4%. Actually, there's another way I could do this where I can actually take this number equals the number of deaths divided by the total number of females. Now think about it this way: if the death rate were, let's say we're in the Middle Ages and people are dying, it's Black Plague and people are really dying in great numbers. Let's say that, for instance, if 10% of the people, the population, died, then this number would come out to be 0.1 or 10%. It came out 0.004 because we're looking at a single type of death, single cause of mortality, and we're looking at a wide range of this population. Okay, so if I were looking at that 10%, that's pretty easy to interpret, 1 in 10 people, right? But when I look at the number I actually wind up with here, that 0.044, 0.004, it's a lot harder to interpret, to wrap your head around that number. So one of the things that we might do is that, like with the 10%, if I said to myself, I wanted to know how many people that represented per 100 people, well, if I take 10% and multiply it by 100, it's 10. In other words, 10 per 100 is 10 deaths per 100 is the same thing as 10% of the people dying. So I'm going to do the same thing here, except since the numbers are so low, I'm going to multiply by 100,000. And we're going to get the number of deaths per 100,000. Well, okay, it worked. It barked at me a little bit, but it worked. Okay, so in terms of females, overall for this entire range, all of these ages, the overall rate of death was 442 per 100,000 people. Okay, that's pretty interesting. Let's do the same calculation for males. So for males, it's going to be equals the total number of deaths over the male population, and again, times 100,000. Okay, so who's more likely to die of cardiovascular disease in New York City, males or females, do you think? Yeah, you would think males, right? I mean, you would normally think males, right? Well, look at this. Something's going on here. Females are dying at a higher rate than males are in New York City. Well, there's a reason why we call that a crude mortality rate. And this is an issue that we wind up with a lot in statistics, particularly in this case, where we're looking at a situation where the difference in these two numbers is caused by a confounding factor in this data. What do you think might cause it to appear that more females are dying? Females are dying at a higher rate in New York than males are. What do you think might cause these statistics to suggest that? You guys online can answer this question also. Anybody online want to hazard a guess? Well,
women go.
Yeah, there's a higher rate of heart disease and cardiovascular disease in women, right?
Men don't go to the doctor.
That don't keep them from dropping dead. This is dead. This is deaths. There's no hiding that.
Well,
That's a hard cap. That's not a matter of opinion.
They're more compliant.
There was a you guys ever I'm showing my age again, but you guys ever watch Monty Python? Or there was a movie that Monty Python made, that the group Monty Python, it was they were an English comedy group that was very popular in the 60s and 70s. And they made a movie about in the 1990s called the Monty Python, The Holy Grail. And in that movie, they're in ancient time, they're in medieval times. And one of them is that one of the things they have is a scene where they're picking up dead bodies during the Black Plague, and they're pulling this cart through town, and somebody's shouting, "Bring out your dead! Bring out your dead!" And as he's pulling the cart, as these two guys are pulling the cart, and people are throwing dead bodies onto the cart, and there's one guy that's kind of hanging out of the cart, says, "Wait a second, I'm not dead." He says, "No, you're dead." So they keep pulling him, and he keeps complaining, "I'm not dead yet." So what do you? So at any rate, as far as this statistic is concerned, there's no opinion here. Like we know that these are right numbers. But what might cause that? Yeah, I'm only half dead, right? Exactly right. So there are a couple of people on here that remember that. Presentation. How about what if who tends to live longer, females or males? Females tend to live longer. So in a population like in New York City, what do you think the distribution of ages might be? You think there's more 80-year-old, 85-year-old females or 85-year-old males? Females, right? What rate? What's the high? What group would you say, age-wise, is the groups that would be most likely to have the highest rates of death from cardiovascular disease? Older. An older population has a higher rate of mortality. What's happening here is that because the distribution by age in New York City is so weighted towards older females, in this population, and they die at such a high rate of heart disease, it makes it look like everybody in that population is at risk when you only look at the crude mortality rate. We need to move that out. Oh, there you go. Okay. Yeah, I have to question you on that also, that like you don't turn your webcam on every once in a while. Also, let me make sure our audio is all muted for everybody. Okay, good. All right, good. I'm back where I am. Okay, so now we need to get rid of that confounding factor, the age. So the way I'm going to do that, this is called direct standardization. Called standardization, this process. But really what we're doing is age adjustment in this case, because the confounding factor is age. So let's get rid of that problem with the confounding factor being age. So one of the things I'm interested in is what's the age-specific death rate, right? For each of these groups for males and females. And how am I going to figure it out? Well, that's going to be equal to this. It's going to be equal to the number of deaths over the number of females in that age range. This one I'm not going to bother to turn into a number per 100,000. And I'm going to drag that down. So I do that for each. Oops. Undo. Okay. We don't need that last one because actually, I'll leave that there. Why not? Okay, so the ones we really want are these ones that represent the rates for each of these different age groups. So I'm going to do the same thing for males. The rate at which males die are equal to the number of deaths divided by the total number of males in that age group. Okay, and there it is for that one. I'm going to actually do these all the way down just to show you that what I'm doing, rather than make it a mystery if I'm dragging it down. Okay, population. And look what happens here. Look at how high the rate of mortality is for both males and females. In fact, if we look at these, the rate for 85-year-olds, whether you're a female or you're a male, right? The rate for 85-year-olds is about the same for those two populations, right? And the rate for 65 to 84-year-olds are very similar, and so on and so forth. So the real difference here is the population. So let me go over here and take a look at this. Okay, so let's take a look at this. So 17% of the female population is in the group that has the highest rate of mortality, right? While 13% of the 13% of the females, I got that wrong. I think those are reversed. That's reversed. There are many more. His population of females that are in that age range, and here's the population of males. So there's many more older females in these two groups than there are older males in these two groups, right? So we could do that as a percentage. I'm going to ignore that. I think there's a little problem with that table over there. But I'm going to ignore it for now because I don't want to get too bogged down. Okay, so now I'm going to take these values and I'm going to move them down here. This is the age-specific death rate, right? Because it's only for that age group and for that gender. So the age-specific death rate for females, I'm going to copy these. I'm going to click in here, drag down through those 4 boxes, say copy, and then go down here to these 4 boxes, and I'm going to say paste, but I'm going to say paste special. And paste special, it gives me a chance to, instead of copying these rows down here, I'm just going to copy the values down because I don't want to be worried about that recalculation and relative addressing and absolute addressing. I'm just going to put the numbers in there rather than the link. I'm going to do the same thing for males. Let's take a look at the age-specific death rate for males for each of those 4 groups. Copy. I'm going to go down here for males. And I'm going to say edit, paste special, and I'm going to save just the values. Thank you. Okay, so I've got them down there, transferred them down there. So now I'm going to say to myself, the problem I had was that our population of females is older than our population of males. So that threw off our calculations for our mortality rates. Now, what would happen if I applied these percentages, the age-specific death rates, to a population that's the same for both groups? Same population of males, same population of females. There's a lot of ways you could do that. You could manufacture an imaginary population where the males and the females are in the same numbers in the same age groups. You could use a different cities population. Well, how about if I just take the sum of male and females, right? Add them all up together and say, well, let's apply this. Let's find out how many women would die in this age range if the population was the sum of males and females in New York City. And the same thing for 45 to 64-year-olds, same things for 65 to 84s, and same things for 85. Now, once I get that expected number of deaths from this population, from this manufactured population, I'm going to do the same thing with the death rates for males. So I'm going to apply my death rates to the same population distribution rather than to 2 different population distributions to see if there really is a difference in the risk of cardiovascular disease between males and females. Let's do that. I'm going to say that, okay, so now I have to multiply the rate times the number of people in that population. And that's the number of people that would have died, that we would anticipate would die if they're dying at that rate. Okay, and I'm going to copy this down again. Whoops. Okay, and I'm going to go over here and do the same thing for males, except this time, for males, I'm going to take this rate and multiply it by that same population. Okay, and I'm going to copy it down. Oops. Not being cooperative, I'll do it the hard way. Fill down. Okay, copies that calculation all the way down. So now I'm going to go get the expected total number of deaths that we would expect for females. Okay, and the expected number of deaths that we would expect for males. Okay, now remember, we're applying the rates that we experience for males and females in different age groups. For New York City, we're now applying them instead of 2 different population distributions, one for females, one for males. We're applying them to the same population distribution to see if there's really a difference in the rate that people are dying within those 2 genders. So, okay, so what's my age-adjusted mortality? Now, this is going to be my age-adjusted mortality rate. So it's going to be equal to the number of women that we would expect to have died at that rate over the population of women. I'm going to multiply that by 100,000 so we can get a number that we can wrap our heads around. Right? That enough zeros? Yeah, I think so. So it's 371. Notice it went down, right, when we adjusted it. Okay, let's see what happens with males. Equals 26,900 over the total number in this population. Okay, and I'm going to put parentheses around this so I can multiply by 100,000. Good. Well, what happened now? Well, now we see that, in fact, males, when you adjust for the ages in the population, if you pull out age as a confounding factor, it's clear that males are at higher risk for death from cardiovascular disease. The reason why it appeared differently with the crude mortality rate is because women tend to live longer, so the New York City population is for women has many more older females in it than there are older males. Okay, so pretty informative, right? We learn now how we can take a confounder and kind of edit it out of our data. And when you go back, if you go back and go back to Google or New York City Department of Health website, if you take a look at those vital statistics, on some of the pages they actually gave you the actual counts or numbers, like the one numbers we gathered here. If you go to other pages, you'll notice that they'll say that they've adjusted the data. The data is age adjusted, or it's adjusted for gender, it's adjusted for other factors, smoking rates or something like that. What they're doing there is they're trying to tease out confounders when they want to focus on certain effects. Okay, so any of you guys ever do this before? How about you guys online? Have you ever tried this before? First time you're seeing this? Okay, good. Okay, pretty cool. I'll put up another example. Like I'll post like it won't be could conceivably something like this could conceivably turn up on the test, but I think it's not that all that likely. But I will put up another example of it, an empty spreadsheet that you can use to compare. You can also do the same thing. I think I have one which is deaths from cancer in Alaska and Florida. And I think, let's see, uh, uh, and I think you'll get see some interesting results on that as well. But I'll give you guys a chance to play with that on your own. Okay. Okay. Oh, the 371? Okay. Okay. That number is D28, which is the expected total number of female deaths divided by the total population times 100,000. Okay. If I had just used the expected number of deaths divided by the total population, it would have come out to be 0.00371. Right? Again, number that's hard to wrap your head around. So it's a little bit more descriptive. Okay, again, once this is processed and we get it uploaded, you'll actually see me type it in again. You can pause it or scrub back and forth and stuff like